Hello, everyone. This is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics Lab. And today I'm going to be talking about correlation and regression, which is Lab 8. So, correlation is when you look at a relationship between two variables, two quantitative variables that are at least on an interval scale, so interval or ratio scaled variables. This is also known as the Pearson product moment correlation, or Pearson R, as denoted by a lowercase r when you're writing the correlation out. Regression is just sort of an extension of correlation where we're trying to predict. So correlation is in both directions, right? So X can lead to Y and Y can lead to X. We're not indicating a direction when we say two variables are correlated. When we say that one variable predicts another, we're indicating a direction. So X would predict Y. Y does not predict X, if that's what we're doing in terms of regression, right? If we're trying to predict Y from X, it's only one direction. It's not both directions that we can say there's a relationship. And prediction is very common in psychology, in any kind of field, really, in the world. I mean, we're always trying to build models to predict stuff. And so what I'm going to be doing here in Lab 8 is I'm going to be using the helping.1 or helping1.sav file. And I'm going to first look at a correlation between helping behavior, which is Z-help in the data set, and sympathy. So is there a relationship? Do they go together? They're not causality, right? They're not causal. So correlation is never a causation, and neither is regression by that same extension there. Like regression is not causation either. You're predicting, but you're not saying X causes Y. Causation can only occur through an experiment. Correlation and regression generally occur with survey data for the most part. So is there a relationship or a correlation between helping behavior and sympathy? And let me just sort of briefly explain other instances of correlation here, just so that you have a background. So X and Y are related. These are interval or ratio scaled for the Pearson R, right? So X can possibly lead to Y in this situation when there's a correlation between X and Y, or Y could lead to X. We get rid of that little mark here. Or another variable we'll call a Z can lead to both X and Y differently, like a triangle. So either X can cause Y, Y can cause X, or a third variable, Z, can cause the relationship between X and Y. That's why correlation can't be causal, because these three scenarios exist and we don't know which of these three scenarios is happening. Right? There's no way to untangle this. So when we say correlation, we're just talking about they go together. Positive correlation, positive R, go in the same direction. So as one increases, the other variable increases. As one variable decreases, the other variable decreases. If we have a negative correlation, they go in opposite directions. So as one variable increases, the other variable decreases. And if we have a zero correlation, that X and Y are not related at all. So examples of these positive correlation is study time and grades. So as your study time goes up, your grades generally go up. That's a positive correlation. A negative correlation would be medication and pain levels. So as you take more medication for your condition, the pain levels hopefully go down. So medication's increasing, pain levels decrease. Negative correlation. Another good one that I always give that are one of my favorites. Social media and grades. As your social media consumption goes up, your grades generally go down. That's one of my favorites to talk about. And a zero correlation means no relationship. So IQ and foot size. Generally, no relationship between your foot size and your IQ, right? If there is, let me know about it because I'm unfamiliar with this, right? It's not like basketball players with their size 18, size 20 sneakers are, all in Mensa, right? All in the high IQ bracket. So that there's not really a correlation there. They're just arbitrary. There's no relationship. That would be a zero correlation. And then we map the correlation on a scatter plot, which is an XY, a graph that I'll show you in SPSS. So we're going to look to see, is there a relationship between helping behavior and sympathy? You'd expect that to be positive, right? Like if you feel more sympathy towards someone, maybe you help them more. Maybe you don't. I don't know. Maybe that's my naivety about the world. Maybe people don't help for that reason, right? So let's look at it. Let's go to this data set. We're going to look at Z help, helping behavior, and sympathy. So here's our data set. Analyze, correlate, bivariate. Bivariate means two variables. We're looking at two variables together. And we're going to look at helping behavior, Z help, and sympathy. Make sure you have Pearson checked off because this is looking for the linear correlation, the Pearson R that we're interested in. Flag significant correlations is good. If you don't want the entire matrix, you can only get the lower diagonal. So maybe we check that off. Diagonal is basically 1 for a correlation matrix. We can leave that checked. Hit OK. And here's our correlation. It's even highlighted here for you. 0.455. Now the range of the correlation coefficient R, Pearson R, is between -1 and +1. The closer it is to either -1 or +1, the stronger the correlation is. This correlation is significant, right? Because it has an asterisk here. Anytime there's an asterisk, it's significant. If there's one asterisk, it's significant at 0.05 level. If there's two asterisks, it's significant at the 0.01 level. This is less than 0.001, so this is very significant. What does that mean? It means it's not zero. There's actually a real correlation here. So it's significant, 0.455. It's moderate. So with correlation, there's a variety of ways to look at it. 0.1 to 0.3 is pretty small. If it's more than 0.3, let's say it's to 0.5 or 0.6. And these are just sort of my guidelines. There's no standard, this is the way it has to be guideline. And I tend to use smaller values for medium because in psychology, correlations tend to be relatively small. They're much higher, the correlations in physical sciences and biological sciences, chemistries, physics, obviously, because there's less error in measurement. So the more error in measurement tends to decrease the correlation magnitude. And in psychology, we have tons and tons of errors in measurement. It's a really difficult field to do research in and to measure things because there's no physical reality, objective reality. Most of the stuff is operational definitions, and people can differ on their operational definitions of certain constructs that you're measuring. So there's a lot of error in measurement, basically. If we're greater than 0.5, call that kind of large. But these are just guidelines. And so right here we have a medium correlation. Not a bad correlation for a psych study. Medium positive, because it's a positive correlation. That means as sympathy goes up, helping behavior goes up. Or as helping behavior goes up, sympathy goes up. We don't know which direction we're going. You could go in both directions. Or there's a third variable. Maybe there's another variable. Maybe it's empathy that leads to both increases in sympathy and helping behavior. Could be a third variable we're not even looking at. That's the problem with correlation, is you don't know what's leading to what, right? I mean, unless you're controlling for all the confounds, the alternative explanations, unless you're controlling for all of that, you don't know. That's why an experiment where you're controlling for everything is the only way you can really draw cause and effect conclusions, because otherwise there's so many variables that can influence both helping behavior and sympathy and drive this relationship. But that's how you do the correlation, and you look for the asterisk to determine if it's significant or not. Let's go back to lab 8. Now that we've done the correlation, we can also try to predict helping behavior using friends problem severity. So basically what we're doing now is a regression. We're going to try to predict helping behavior using the severity of a friend's problem as the predictor. Once again, this is not causality. This is just giving a direction. So as severity of your friend's problems increase, helping behavior probably will change, probably will increase, right? So we're giving a direction. So it's not a correlation because we're giving a direction. We're looking at severity of the problem, predicting helping behavior. So how do we run a simple regression like this? This is a bivariate regression. Same thing, analyze, right? We want to go to analyze regression down here. And we want to go to linear. Linear is the most common regression because it's much easier to explain a straight line than it is to explain, a parabola or a cubic or a quartic or a quintic, equation. It's very hard to explain higher order curves. It's much easier to explain a line. So we're predicting helping behavior. So the dependent variable will be z help. And we're using severity of a friend's problem as my predictor. So the predictors go into this box called independent. Then hit OK. And here's our regression. So this R squared is the proportion of variance in helping behavior that is predicted by the severity of your friend's problems. So what this is saying is that 8.5%, if I turn this into a percent, 8.5% of helping behavior is explained by how severe your friend's problem is. That means that 91.5% of helping behavior is not explained by severity. It's important to notice. Is this regression significant? That means, is it greater than 0? Is it explaining more than 0? Well, take a look at it here. This ANOVA, it explains more than 0. It's significant. 0.008, less than 0.05. That means it's explaining more than 0% of the variance in helping behavior. So this is basically saying that 8.5 is significantly greater than 0. Does that really tell you much? Well, if it's 0, it's a problem, right? The model is garbage if it's explaining 0 of the dependent variable. This is explaining more than 0, but it's only explaining 8.5%, which is not a lot. And this is the equation for the line, for the regression line. So if you're drawing the regression line, we would call this y hat, or y predictor, or y, I'll put y little apostrophe. A lot of times you see y hat, but I don't know if y hat is, it's probably here somewhere in Microsoft Word, but I don't see it here. So predicted y is equal to, now this is the general equation, is bx plus a, where b is the slope of the line and a is the y-intercept. That's the general equation for the regression line. Right. In this situation, for this particular example, you got y prime is equal to b. So you want to look for severity, and you want to look under capital B, unstandardized coefficient. That's where your slope is going to be next to severity, because severity is the predictor, right? Independent variable. So the slope here is 0.287. So this will be 0.287 times x, whatever your x is. You plug in x to make the line, right? Plug in x, get y. So it's 287 times x, right? So I'll write it like this. I'll actually put parentheses around it just to make it cleaner. Plus the y-intercept. The y-intercept is where you see constant. Constant, you look under this capital B, it's negative 0.907. So it's plus this constant. It's plus negative 0.907, which simply becomes minus 0.907. And this is your regression line for this problem. 0.287x minus 0.907. Now, if I were to come up with the regression line, that's the regression line. If I were to come up with a predicted value, so let's say I wanted to predict helping behavior for a severity of 10. So if severity of the problem is 10, what is the helping behavior going to be? Well, we'd plug 10 in here. So it'd be y prime, or y hat, equals 0.287 times 10 minus 0.907, and we'd solve this. So it'd be 0.287 minus 0.907. So let me just do that quick on the calculator. So that'd be 2.87 minus 0.907 gives me 1.963 as my predicted helping behavior. Now that's the value on the line, on the regression line. That's the predicted value. So we predict that helping behavior would be 1.963 if severity is 10. So that's the actual value on the line. Can we sort of show this relationship between severity and helping behavior? Well, yes, let's make a scatter plot first. So let's do graph scatter, simple scatter. And we'll do a graph here showing the relationship between severity and helping behavior. Severity is x. So put severity as x, put z help as y, hit OK. And this is the relationship between severity and helping behavior. I'm not a fan of these lines here in the scatter plot. I want to see if I can remove them. Grid lines. It's not letting me. I'll leave them for now. I'm just not a big fan of these grid lines. They just kind of annoy me. But I'm not sure. There's probably a way to remove them easier than I'm doing it right now. Okay. So that's the scatter plot. What I do. This is the scatter plot. This is a scatter plot shows the relationship between two variables. The two variables that are correlated. And these two variables are correlated, not super strongly, but this is the relationship. So you can find each of these circles represents one individual score on severity and their corresponding score on helping behavior, right? Now I want to put the prediction line in here. So I got to add the regression line to this. So I'm going to have to find add reference line, because I don't think fit line at total will work. Add reference line. So after I double click on this, it brings up the editor, and I can just click this little reference line here, right? And this is not the regression line. I need to type in the regression line. So the regression line, as we said before, is positive 0.287 times, gonna put times in there, it doesn't understand parenthesis here, times x. So 0.027 times x minus 0.907, right? And there's your regression line. See how the line changed? It becomes my regression line. So now, I don't know why it keeps shutting this off when I close it. So now I can look at this regression line, and this is the prediction line. So 10 is a little bit off of this chart, but I can predict any value here. And I can plot the value of the line. This is my prediction. The dot is the actual value for helping behavior at a given severity level. The dots are the actual values. The line is the predicted value. And you can see how far you're off. So if the dots are far from the line, then you have a lot of prediction error, right? And we see dots that are closer here somewhat, right? A little bit close here, but then get a little bit further away from the line here. So the line is doing an okay job predicting, but you have a lot of variability around the line. So like not all the points or not all the scatter plot is right around the line. It's kind of all over the place here. So it's telling me the line is doing an okay job, but it's not great. And that's kind of what I told you before when I looked at the model, 8.5%. This line is explaining 8.5% of the variability in helping behavior. So that's something, but there's 91.5% that's not explained. What does that mean? That means there's other variables other than severity that play a role in predicting helping behavior. So you would need to add other variables to try to predict helping behavior better than just using one variable. But we are starting with one variable because it's easier to explain. It's easier to process. The slope of the line is positive, which means as severity increases, helping behavior is increasing, and that makes sense. But the line is not a perfect fit for this data because this data is kind of spread all over the place. So there's probably other predictors that are better than just severity. And that's what this graph is telling me here. And this is basically the graph that I've made in the instructions. Now, look, you can look at more than one predictor. And if you look at more than one predictor, you have something called multiple regression. So let's take a look at Z-help. We're going to predict helping behavior by using severity, anger, and sympathy. So let's add to this model. Analyze regression, linear, same thing. But we're going to add severity. We're going to add anger as another predictor. Anger. And sympathy. Well, no, sympathy we did. No, sympathy. And we're adding sympathy. Sympathy regards to a friend's problem. So if you're angry, if it's a severe problem and you're angry about it and you have a lot of sympathy for your friend, are you going to help more? So all three of these. So I have three predictors and I have one dependent variable, which is helping behavior. Hit OK. Now look at this model. It went from 8.5% all the way up to 31.6%. That's a huge jump. So that's a big increase in terms of the predictability of the model. That's the R squared here. We're at 31.6%. Is this model significant? Yeah, it's very significant. It's a lot better than the first model. The F is 11. It's less than 0.001, the significance value. That obviously is less than 0.05, so we reject the null. And we say that the model predicts more than 0, and it does. It predicts 31.6%. It's a pretty good model. I'd be happy with this, research-wise. Now, what do these variables sort of indicate? So go down to the coefficient. We are going to have a line here. But this line is going to extend into hyperspace. So I'm not going to be able to graph this because we have more than 3 dimensions here. So with one predictor, we have 2 dimensions. With 2 predictors, we have 3 dimensions. With 3 predictors, we have 4 dimensions. So this would be a line in 4th dimensional space, hyperspace. What does that look like? I have no idea. It looks like a line in 4th dimensional space. And these are the slopes of, basically the slope of the line in each of those directions. So you have the slope in the second dimension, the length width dimension. Then you have it also in the third dimension and the 4th dimension. So it's kind of hard to interpret the coefficients. But I could write out this regression equation. I wouldn't be able to visualize it, but I could write it out. So this equation here, this multiple regression, would be predicting y is equal to severity. Now these change because severity changes because I have other predictors here. So it'd be times x, right? Plus 0.274 times y plus, I wouldn't be able to call this y hat though. I'd have to call this something else because I have an x, y, and a z. So let's call this actually, let me call it y hat and just put it in so don't make it too confusing. I'm just going to put in the variable names because we won't know what y and z are here. Anger. So 0.130 times severity score plus 0.274 times anger score plus 0.488 times sympathy score. And that is your multiple regression equation. So you need to have a score on severity, a score on anger, and a score on sympathy, and you plug them in. Actually, I forgot to add the constant, minus 2.987. There's your multiple regression equation for this. Obviously, I'm not going to ask you this for a lab or for the exam. It's just an extension of the bivariate regression to more than one predictor. And in the real world, we do this all the time. We can't graph it, but we do it all the time, right? But this is what it'd be in 4th dimensional space, whatever that looks like. That's the regression prediction. That's a prediction line with 3 predictors. Now, other thing you want to look at are these is the impact of these variables greater than 0? So severity, and you see that with the significance value here. So severity is pretty small, it's 0.130. Is that significantly different than 0? So does severity really help with the prediction more than 0? More than the default, right? And 0.192 says it doesn't. The severity is not that important here. The two significant predictors here is anger and sympathy. They're both less than 0.05. And if you want to look at the relative strength of them compared to each other, you look at this thing called standardized beta. The bigger this value, the more important the predictor is. As you can see, the two significant predictors are 0.300 and 0.445, and the one non-significant predictor, severity, is 0.132. So that's showing you that anger and sympathy are much more important predictors of helping behavior than just severity of the friend's problem, based on this multiple regression model. And that's the multiple regression equation, how to do multiple regression. Now, we're going to look here at the correlation between trauma and life satisfaction. So let's look at that. Analyze by correlate bivariate. Let's look at trauma and life satisfaction. So we have to find trauma. I don't see trauma in here. Okay, we got to look up we have to open the divorce.save file first. So that's what I'm doing wrong here. Divorce.save file. Let's open the divorce.save file first. It's already open. This is the helping file. This is not it. So here's the divorce.save file. Let's see what we're looking at. Trauma, life satisfaction, and trauma. And then age and life satisfaction. So let's look at that. So analyze correlate bivariate. So trauma and life satisfaction. And then age. We're going to throw age in there also. So we'll all three of these, right? You put all three together, show lower triangle, show diagonal, flag significant correlation. Make sure Pearson is checked. Two-tailed, of course, hit OK. And here are our correlations. So between trauma and life satisfaction, it's a negative correlation. And it's a negative medium-sized correlation. And it's significant because you see the two asterisks, that means it's significant. It's different than 0. So as trauma increases, life satisfaction goes down. That makes sense, right? How about age and trauma? If you look at age and trauma, you go down and you find trauma here, you find age on the left. Negative 0.070, it's not even significant. 0.293 is not less than 0.05. It's not even significant. There's no asterisk. So there's no relationship between trauma and age. And then life satisfaction and age, it's also not significant. 0.054. P-value 0.418, not significant. Create a scatter plot of age by life satisfaction. So let's take a look at that. Age and life satisfaction. So we're going to do graphs, scatter. I'm going to do simple, age and life satisfaction. So let's do age on the X. Let's do life satisfaction on the Y. Hit OK. There's our scatter plot. And it looks like there's no real correlation here. You know, there's no, if I were to draw the best fitting line through this, it'd be kind of horizontal. And the slope of a horizontal line is 0, so therefore the correlation is near 0. There's no real pattern here. It's not like as age goes up, life satisfaction goes up. The dots are kind of randomly scattered here, which suggests a correlation of 0 or near 0. And that's what we get. We get 0.054. It's almost 0. So that makes sense. Predict life satisfaction from depression. Let's do life satisfaction from depression. Analyze regression, linear. Predict life satisfaction from depression. We just use life satisfaction. So that's dependent variable. Depression's our independent variable, our predictor. We got to find DEP. Let's see if I can find it this way. Right here. Depression predicts life satisfaction. We see a very small correlation, and it's only showing 2.5% here, right? That's not a lot at all. It's only explaining 2.5% of, if I'm using depression as a predictor of life satisfaction, depression is only predicting 2.5% of life satisfaction here. Is it different than 0? Is 2.5% greater than 0? It is 0.016, so it's significant. So it's predicting more than 0, but it's only predicting 2.5%, which is very, very small. Not a very good predictor. What is the line of the prediction, the regression line here? Y prime is equal to negative 0.079 times x plus the y-intercept. So we look at the unstandardized coefficient here for depression, negative 0.079. That's our x times our x value for depression. Whatever your depression is, that's the slope. And the y-intercept is positive 5.129. And that is our regression equation predicting life satisfaction from depression. But it's a pretty weak, very weak model, very weak predictor. Calculate multiple regression, predicting life satisfaction from depression, age, and trauma. Depression, age, and trauma. So once again, analyze regression linear. We have depression, we need age, and we need trauma. And we're hoping it's going to be a lot better than just depression, because just depression didn't work. Hit OK. We don't see much. This is not much better. It's 10% of the variance. It's not much better. It's a little bit better. It's 7.5% better, but it's not tremendously better. I mean, that's still a very weak model here, even with trauma, age, and depression as predictors of life satisfaction. The model is significantly different than 0, which the SANOVA tells us. So it's a significant predictor. You could write the F value and the sig value for that, right? In terms of the coefficients, significant coefficients are only trauma. So it looks like trauma is the one that's predicting. Age and depression are not even significant predictors in this model. They're this very, very minuscule impact here. If I look at the standardized betas here, the biggest value by far is trauma. And trauma is negatively predicting life satisfaction. That makes sense. So you have more trauma, your life satisfaction is going down. And that's so much bigger than these, right? The sign means nothing. It's just the magnitude. So look at the absolute values of these. Trauma is a huge predictor, and age and depression are doing almost nothing here. They're not even significant. They're not even better than 0. So they're not really adding anything here. It's mostly just trauma. So it's a pretty garbage model. The only thing here worth keeping would be trauma. I would drop age and depression as predictors of life satisfaction completely and look at trauma in combination with something else, because age and depression are not really predicting anything here. And that's how you do correlation, regression, and a little bit of multiple regression. So hopefully that helps you out. And if you have any questions, see me. If not, see you for the next one. Bye for now.